So hello, welcome to my talk. I know it's a pretty sad day for hash functions, isn't it? No, the merge, proof of stake. They're trying to kill hash functions. The people hate hashing. It's bad for the planet, but they won't succeed. We'll keep on hashing stuff and hashing in plenty of ways, and this is the topic of my talk: hashing and fast hashing. And the great news is that we have some time, I think. So Ari, that's the last talk of the session, right? So we have. The conference finishes at 6:30. It's 3, so 3 hours of hashing. So hashing is everywhere, not just hashing one message, but doing a lot of stuff with hashing, and in ZKP, in ZK proofs in particular. So commitments. In every single talk today, you hear about commitments, polynomial commitments, and so on. You hear about Merkle trees. When you don't know what to do, you use a tree. The Fiat Shamir, of course, when you want to turn a protocol from interactive to non-interactive. You hash stuff. And of course, when you want to generate to make things unpredictable, like in Fiat Shamir, and just for simple hashing, of course, pseudo-random functions, pseudo-random permutations, to some extent DRBGs, so deterministic random bit generators, XOFs, extensible output functions. So there's so many hash functions, I don't know myself all of them. And if you look at a snark, at a protocol, so like Aleo, so you have hashing everywhere. If you look at Starks, you have even more hashing. So I don't need to convince you that what is Ethereum people are trying to do, killing hashing, they won't succeed. So I've been designing hash functions for quite a while. So this is a joint talk, a joint work with Dmitry, who is here, and the main instigator of this project. And more than 10 years ago, in 2008, 2007, so Dmitry and I were doing our PhD and working on hash functions, trying to break hash functions, and then we designed some hash functions with more or less success. And the game at the time was to make hashing faster. And faster meant, well, you implement it in software, in C, you're an academic, you don't write very good code, but you try to make it as fast as possible, and you measure in terms of cycles per byte, to make it independent of the frequency. But in the ZK Summit context, we don't only care about the speed of vanilla hashing. So vanilla means when it's run as it's specified, not in a circuit, not in terms of constraints or error or R1CS, you name it. But in the context of ZKP, the performance matters even more than the speed in pure software, because people were spending days trying to make their hash a bit faster, hashing at 10 gigabytes per second instead of 8 gigabytes per second, and then we're faster. Man, look at the read and write speed of your drive. Look at your bandwidth. Look at your network speed. You don't care about being 10 gigs or 20 gigs. It depends. But so in the context of ZK proofs, an important metric is the number of constraints. So be they R1CS, like in Marlin, or air, or other types like in Planck and all the Planck family. But in general, if you have many R1CS constraints, you will have many IR constraints as well. So that's what is sometimes called algebraic complexity. And of course, the goal is to minimize the cost, the proof generation. And if you use a general purpose hash function such as Blake2 or SHA-256, it won't be ideal, let's say. So that's why people came up with the concept of ZK-friendly hash functions. So functions that would be well suited for the use case of ZK proof systems, where most of the time we work with algebraic structures, so hashtag finite field, typically, polynomials and so on. But most of the time, you're going to work with objects that will lie in a finite field. And for example, something that is straightforward in a normal computer, like the XOR operation, the most stupid operation of all time, then it's quite painful to do on finite fields, because you have to think in terms of encoding, in terms of converting your finite field representation in terms of XOR, and that leads to many constraints, and that's very annoying. But at the time when I wanted to implement Blake2 in Leo, so the language of Aleo, I was stuck at the part where I had to do XOR. I was like, damn, okay, it doesn't work. So, even though I like Blake2, I don't hate Blake2, of course, I designed it. It's really not what you want to use if you are going for an efficient circuit, an efficient proof generation. So people came up with a bunch of designs. Poseidon is the most famous one. So one of the co-designers, Dmitry, is here as well. And Poseidon is orders of magnitude faster and smaller than Blake 2 or SHA-256. So Poseidon was designed, I believe, in 2019, right? Whereas Blake 2 was designed in 2012, it depends how you count it. And SHA-256 was designed even earlier. Some people are making the argument that Poseidon and other algebraic hashes, they're a bit new. They're not as well studied as the other ones, so we want to stick with SHA-2 and Blake 2. But I think Poseidon is safe, at least the parameters that are defined. So of course, another way to make hashing faster is, just to reduce the number of computations, reduce the number of rounds. So from my perspective, many hash functions are also over-designed, but that's another question. So let's go back to Poseidon. You see it's used in Aleo, Nomad, Dusk, Falcon, Penumbra, you name it, many projects. But people designed other hash functions, such as Rescue, such as Griffin. Neptune is a variant of Poseidon, MIMC. So sometimes to optimize maybe for the field size or to optimize for the constraint type. So if you see, there's also Synsemilia by the Zcash people. And if you just look at the numbers here, so Blake 2 SHA-256, not ZK-friendly hashes. Big numbers here in terms of error product, in terms of R1CS or lookup constraints. And you see there's really, an order of magnitude between these guys and ZK-friendly ones. Okay. But they're fast natively in the vanilla mode. So ZK-friendly hash is good. It's presumably secure. It's presumably efficient. And it often works like this. So it's a sponge function. Do you know what a sponge is? So it's a sponge function instead of hash function, but it's a bit misleading because ultimately a sponge function gives you a hash function. It's a way to construct it. So it's a very simple way. Instead of having to design something that takes something big and shrinks it to something small, you just design a permutation. So something that maps, in a reversible way, an input of some fixed size. So in Ketchak, it's 1600 bits. And in Poseidon, it depends. But it's easier to design as a cryptographer. So you look at the block cipher. It's a permutation with a key. You remove the key, you get a permutation. So you take your block cipher, you remove the key, you get a hash function. And with this permutation, you can create a hash, but you can create other stuff. But the way it works is that you just XOR your input in, you permute, you XOR, you permute, you XOR. So of course, you just XOR part of the state, not everything, otherwise it's completely broken. And there's another mode that is called duplex. So here, you don't just send input and collect the output. You can combine the two. You inject, you absorb some input, and then you read. And then you can write, and then maybe you want to read to get some output. So the typical use case for this is a PRNG, whereby you get entropy from your system, you introduce entropy, and the read option is when you get a syscall or whatever that needs some sort of random bytes. So maybe you can also think in terms of Fiat Shamir at this point, okay, I write my commitments, and I read my challenge, and this kind of thing. And you see the word pad. So pad means that you have to encode your input in a certain way, and pad means adding some additional data, for example, the encoding of the size of your input to get the security proof working and to get a secure design. But in practice, it's not so easy to do. I told you it's easy, and then I tell you it's not easy. Okay, what is this guy saying? So in crypto, like many times, it depends. It's deceptively simple in the sense that once you have to implement it, there are many questions that come to you. Like, well, the encoding, the parameters, the interface, how do you define the API? You take 5 different implementations of Poseidon, you get 6 different APIs. 6 different ways to encode the input, to assign the arguments to the input. And also what we call the domain separation. So if you have objects of different type, of variable size, you need some encoding to say, this is the start of my first object. Now I'm going to the second object. And maybe there are different types of objects. And you want to avoid trivial collisions whereby if you have an object of 2 bytes and an object of 1 byte, then you can also see it as one object of 1 byte and another object of 2 bytes. But if the 3 bytes have the same value, then in these 2 situations, you end up with the same hash. So domain separation is quite important. And the padding, so in the real world, in the vanilla case, non-ZK, we don't really care. But in the ZK space, every single optimization is useful because something that looks small on paper can translate in terms of hundreds of constraints. So there are simple ways to simplify it. Some people started specifying the hash function in terms of field element instead of bits. So there are some papers that talk in terms of algebraic capacity. So the capacity concept in a sponge, the capacity is the size of the part where you don't write and don't read. And just define it in terms of reading and writing field elements. And also, if you assume that the input has a fixed size, so you take a Fiat Shamir, you know in advance the number of elements that you're going to provide, you know their size, because the size of your field is not going to change, well, normally. So there's a lot of things specific to the ZK use cases that we can leverage to simplify out the designs. Okay, so maybe you don't trust me, maybe it's FUD, it's not that hard. There's no bugs in hash functions. So to prove that I'm right, I did the following experiment a few days ago when I did my slides. I picked a uniformly random Poseidon implementation on the GitHub website. Well, not uniformly random because I picked on the first page or second page of the results. And I gave myself 5 minutes to find a bug. Quite challenging. I was like, oh, shit. But the first implementation, I didn't find any bug. I looked for the usual stuff, domain separation, and even sometimes people confuse matrix vector and vector matrix product in Poseidon. But the first was fine. And in the second implementation, which I will not cite because it's from a friend, I found a bug. And it was, what I can say is that they were trying to implement multiple instances of Poseidon to support multiple instances and to estimate the security level depending on the parameters. The parameters being capacity, rate, and width size of the state. And the computation was wrong. Was wrong in a way whereby they overestimated the security. If I remember correctly, they derived it from the width, not from the capacity. So you could get an instance that the program believed was maybe 128-bit secure, whereas it was not. So, well, the upshot is that even very smart, experienced people can get stuff wrong. If I write crypto code, I will get stuff wrong all the time. So we need to minimize the risk, minimize the errors, and bring what the people need, safe. Sponge API for field elements. It's not a new hash function. It's just a way to simplify, standardize the boring stuff. So where an implementer, the API, the encodings, all these things that you hate doing because it's not really cool, it's not really interesting, it's not really deep mathematically, but it has to be done. And we also get rid of the padding. Do you know that in terms of padding, there's SHA-3, there's Ketsak? You might think they're the same. No, they're not the same. Because the padding is in SHA-3, Ketsak is not the same padding as not SHA-3 Ketsak. And I think that in Ethereum, they use the non-SHA-3 Ketsak, so the old padding. Yeah, okay. So see, crypto is so confusing.
And launched like 3 days before NIST did the standards with the padding.
Really?
Yeah.
Oh.
Or like, not even 3 days, it was like
blame NIST.
30 hours. It was,
So yeah. So no padding, no problem. We get rid of the padding. It doesn't come completely for free. We have a workaround. We use what we call I/O pattern, which is essentially a description of the calls you're going to make. So you might say, I want to absorb 10 bytes, and then I want to read 2 bytes, and so on and so forth. And it will be beneficial to everyone if it's kind of de facto standard because it will make implementations interoperable. It will give a common baseline to implement this kind of hash function. And also for people who are interested in hardware, so what Omer presented this morning, I think it will also be easier if we have a single way to do hashing so that you don't have to create a new chip for every single hash function use case. So then again, it's not anything very deep or new. It's not a completely new mode. It's just a twist over the duplex mode. And it's not a new permutation. So there are a lot of good works in the permutation space. I think Dmitry will present a new one in 45 minutes. But the flip side is that you can use any permutation with safe. So you like Poseidon, use it. You can use any finite field. So our goal is to be as generic as possible. So the API has to be quite simple. So there's essentially 4 calls. Start, where you initialize the sponge. So it looks a bit complicated, IO pattern, domain separator, but the IO pattern is just a description of the calls you're going to make. Again, so absorb, squeeze, absorb, squeeze with the size. And domain separator is just a fancy name to say, personalization or another string that will make the function different. So if you have the same IO pattern and different domain separators, you will get different initial values, which means that the functions will behave completely differently. For any same input, you will get completely different output. So absorb and squeeze, it's write and read, as I mentioned. However, the difference is that you can provide arbitrarily many bits to each of those calls. So if the rate of your sponge, so if what you can write between 2 permutations is, I don't know, just 3 bytes, you're not limited to 3 bytes here, because it will distribute whatever you have to read or write across as many small absorbs or squeeze as possible. What I want to say is that if you look here, if I can absorb 3 bytes per call, I can do 3. So you can call our absorb with 9, and it will take care of doing the 2 permutations. And likewise for the squeeze. Okay, and finish is the conclusion. So why do you need to call finish if you can just squeeze stuff out and call it a day? So finish will do maybe 2 things. So it will erase the memory. Right? You want to use the mem0 or equivalent to safely erase the memory to make sure that nothing is left in your cache or whatnot. And it will also verify that all the calls that have been specified by the IO pattern have been executed. So the goal is to prevent what cryptographers call misuse. Maybe you define your function in a way that you have to do another 3 absorb calls and write and read at 10 bytes. And the finish call will validate that all the calls that had to be made have been done with the right length parameter. So you can see it as a safety net in your protocol to ensure that you have used this correctly and that you computed the IO pattern correctly. And there's no padding at all, no reason to pad stuff. No, but there's a caveat. So the state, it's stateful, of course. You have the permutation state, so it's the elements of your permutation. It might be 4, 6, 8 more field elements, depending on the size, depending on the security level. The permutation, of course, so the function that will permute the elements. And 2 counters, so just small numbers between 0 and the rate, so they can be 8-bit values, positive 8-bit values. And then we also need a hash function. You're like, okay, why do you need a hash function for a hash function? It's just to bootstrap the design, so when we compute the initial value, we take this IO pattern, so this encoding of the usage of the hash function. We encode it with a very straightforward serialization system, and we hash it down to 128 bits to write these 128 bits in the initial value. But you don't need it at runtime. You can just pre-compute because you will know in advance what you're going to hash, what you're going to read and write. So this can be part of the design. You don't even need to have it as part of your code. You can pre-compute the initial value, and you won't need a hash function at all. And likewise, the tag, the initial value, is derived from the use case, but you can also hard code it even in the code. And so that's what I mentioned. You derive it from the I/O pattern. And just to give you an example, I'll be repeating what I mentioned before. So there are 3 I/O patterns. So the first one, you absorb 3 bytes, no, 3 elements, sorry. You see, I'm not in field mode, I'm still thinking in terms of byte. You absorb 3 elements, and then you read 1. And in this case, you absorb 2 elements, and you read 1. In the third case, you absorb 2. Then you absorb 1 again, and you read 1. So which ones are equivalent to each other? Sorry?
1 and 3.
Right, 1 and 3. Because here you're going to absorb 2 plus 1 equals 3, and here you're going to absorb 3 in one call. But for the safe mode, it will be equivalent. So it will aggregate these 2 values, and it will just see this as one single absorb with 3 elements, which means that you're going to have the same initial value, which means that you're going to have the same output at the end. So you have this degree of flexibility in how you organize your calls. So you can see start as committing to your I/O pattern, and then the finish as verifying the commitment, as opening the commitment. Yeah. Okay. So then you can see this thing we did as a middleware between the applications and the sponge function. And the sponge, if you have, I don't know, Poseidon, Quetzalcoatl, or whatnot, it can or it should only expose this very minimal, low-level API where you initialize the capacity with the initial value. You permit, of course, and read and write elements. So you can read or you can add. And you don't need anything else. Whoops. I/O problem? Absorb somebody. Okay. Switch on and off again. Can't signal. Okay. So let's move to concrete use cases. Will be very straightforward. So Merkle tree, the simplest Merkle tree you can imagine, 2 leaves and 1 root. So each leaf is 1 element. So you absorb the first one, you absorb the second one, and then you squeeze out 1 element. But before that, you'll have defined your initial value, and then you verify that it is correct. In the paper, we provide some test values using the SHA-3 256 hash functions if you want to verify it. So that's the case of a basic, non-interactive to interactive protocol. You have some elements of the proof, or some typically commitments. The prover commits to these 2 values. Then the verifier will send some challenge. So in terms of safe, in terms of sponge, this will be an absorb, this will be a squeeze, this will be a read, then a write, then a read, and so on. Okay. So some limitations of this very nice mode that we designed. Maybe the first one is it doesn't support what is sometimes called variable length input. If you don't know in advance the size of your message, then you cannot define the I/O pattern. Therefore, you don't have an IV. So you can hash. So it's a use case that sometimes happens, but we specify how to handle it. You will most likely need some padding, but you'll be better off if you know the size in advance. You will have less overhead. We even describe a way to use what we call an infinite length PRNG if you don't know when or if you're going to stop generating output. If you have already this stateful system where you will read forever, that can also be done. It's a small workaround, and likewise for the AEAD, so authenticated encryption with associated data. You have workarounds to support input when you don't know the size in advance. So yeah, I just showed Merkle tree, Fiat Shamir, but of course you can do PRF, aka MAC, encryption, authenticated encryption, simple hashing, everything you can do with a permutation. Also the input domain separation that depends on your protocol. So let's say you hash stuff. You hash a field element, that's fine. Then you need to hash a string. So you have to encode your string into a field element. But then this becomes a field element, but you're hashing a string. So you have a collision between the case I hash a field element and the case I hash a string, which happens to have the same encoding. So you might want or need, well, it depends, to add some encoding to signal the type. You can add an extra byte, you can add an extra element. So then it really depends on your protocol's constraints and specifically what is controlled by the attacker, what is potentially, modifiable by the attacker, what is determined in advance, what is random. So there's no single right answer here. Also, you need a hash function like I mentioned before, but it's not a problem. We have good hash functions. And maybe last point that people raise is, but where's the security proof? Dmitry and I are very convinced that it's secure. So shame on us if it's not. But more seriously, I don't like writing security proofs. Some people do it very well. The change compared to the original design is very small, and it will be fairly easy to show that our mode with the IO pattern instead of the padding has exactly the same security bound as duplex and whatnot. And I think some people might be working on it, right?
Yeah, so work in progress.
Work in progress, yeah. So proof in the full version of the paper, as we say. So yeah, if you'd like to learn more, we have a page online, a HackMD page. The reference code is Filecoin's implementation in the Neptune project, which is a small twist over Poseidon. So if you're a hash function designer, you can focus on creating a permutation, which is by far the hardest part, and just reuse this mode for the rest. If you're specifying a protocol, it will help a lot the implementers to specify to write it in terms of safe calls, absorb, squeeze, instead of having different terms, different notation, different language. Also, it will make the code reviewers very happy. And implementers likewise, so if you have to code it in software or hardware, might be convenient to use the same wording, the same API, this IO pattern, because it will also make your library interoperable with people who choose to use the same protocol. Okay. So we'd be happy if it becomes a de facto standard. We don't have a certification program or, do this at your own risk. So thank you for your attention and here for questions. Yes?
Would it make sense to use safe in the context maybe of MPC, where you're also handling like messages and so on, or is this really made specific?
For like MPC in the head or?
Yeah, or even just like multivariate computations where you kind of know the messages you're getting, or would I just use strobe or one of those?
Yes, so you can see strobe as a generalization of a sponge. So it's a stateful object where you can write and read stuff. Here our goal is limited to emulated some symmetric primitives. But if you are in a case where in an MPC case where you want to commit to stuff, you have this concept of challenge response. It can also work very well because it can save you from having to choose, okay, what I'm going to hash. Because I've seen many bugs where, you had to hash a transcript, and people were forgetting to put stuff in the transcript. So there are many bugs in TSS, in threshold sending protocol, where, okay, that's what we hash, that's what we hash. So if you have something that is stateful and that is hashing, is absorbing all your transcript in the first place, so you have the guarantee that you're not going to forget any value in your hash. So that's actually a good use case we could have mentioned, yeah. Threshold sending.
Do you imagine using this with Fiat Shamir, like every round it's absorbing an approval message, alpha, challenge?
Sorry, I didn't understand. Yeah, okay.
For general hashing, is Fiat Shamir your primary interest for this, or
Oh.
is this
No, for any application. So Fiat Shamir just happens to be one relevant use case, but and also Fiat Shamir is not the only case where you need to read and write. But
Sorry, I might have missed this, but so the overhead inside of the stock would just be one extra multiplication when you have the hash output and then multiplied by the hash.
No, actually, you don't have any overhead because all these I/O patterns is just hard-coded constants, so there will be constants in the circuit. So you have to just.
So compared to like a cited implementation where I just like implemented cited from paper, this would it would just have one extra.
yeah.
It will just you just have to call Poseidon like in certain ways, but it's no extra overhead. It's the same cost. You just have to like code with proper input, like initialize it properly.
Yeah, it's pre-computation, so it's not runtime cost.
It's pre-computed, so there's no extra startup cost.
Yeah.
So inside the stack, the way that the stack would change is it would have the minimum multiplication by also.
Multiplication where? Sorry.
Wait, so what is done with the output of the hash function, which like
I just copied to the IV.
okay.
So you see that you pass the hash output as field elements. So if it's 128-bit and you have 128-bit field, you have one. Otherwise, you pass it at 2 or 3, and then you just copy paste it in the.
You mentioned that this could use any arbitrary underlying field.
Yeah.
How are fields selected and like the field that you're going to
Well, typically it should be a crypto-friendly field, where the discrete log problem is hard, and typically a large prime order field. Because if you want a binary field, then Blake is fine because it works with bits, which are, GF2. But yeah, it's typically the main use case is it's at least 64-bit fields, and most commonly 256 or more.
Cool. And where is the field? Where would you declare or define the field that you're?
Yeah, good points, because we don't depend on the field. We don't encode the field. But we don't need to, because if you have a different field, the function will behave differently. The operations will be different, so you will get a different input, a different output, sorry. So that's why you don't need to explicitly say, I'm using this field or this group or this.
Makes sense. And then does the input need to be encoded to a field element as well?
Yep.
So you can do the field.
Exactly. And that's the part where if you need to hash objects which are not natively field elements, you need to convert them to field elements. And if you have some ambiguity.
Hash to field almost, like hash to
Yeah, right, yeah. So it can be straightforward, but these straightforward problems are sometimes the ones that people get wrong. So you want to avoid collisions and two different items mapping to the same field element.
And that depends on that responsibility of hashing to field is on the person who's using.
Yeah, the caller, the application, because well, we can anticipate what people will need, if it's strings, images, or whatnot. Yeah.
And for this IV, can you also like hash other stuff, like for example verification key or something? Is that like the intention?
Oh, you could put whatever you want in the initialization. We have this domain separator, which is a generic input type specified as a string of arbitrary size, which is just appended to the I/O pattern. So if you have, 1 gig image disk, you may want to hash it as well. The good thing with hash functions, you can hash as much as you want. Yeah. Okay. So if no other questions, thank you guys, and hope you liked it.